Okay, um, this is only one page here, but on this page we have a flow chart, and this flow chart shows the relationship of different numbers within a complex number system. So what does this flow chart represent? Well, we can look at this flow chart, either from the top down or from the bottom up. Let me try and maybe start from the bottom up, and let's see how that goes. So at the very bottom, we have a type or a category of numbers called natural numbers. Natural numbers are sometimes referred to as counting numbers. All right, and they're called counting numbers because, when you go to the store and you buy some apples, um, you just start counting how many apples you've got. 1, 2, 3, 4, 5. So counting numbers, natural numbers are just like if you were counting the number of something that you maybe hid in your bag. So that's an example of a natural number. Now, if you take the natural numbers, notice the natural numbers do not include 0. So you typically wouldn't go to the store for apples and count 0 as like 0 apples. You would just take one and say, I've got 1, I've got 2, I've got 3, I've got 4. So if you take the set here of natural numbers and you add 0 to that, then you have the natural numbers and 0. And this set of numbers that includes 0, these are called whole numbers. So when we talk about the set of whole numbers, it's 0 plus the counting numbers. So 0, 1, 2, 3, 4, 5, on into infinity. Now notice that what's missing is that the whole numbers are missing negative numbers. So if we take the whole number set, and so if we take the whole number set and we add in negative numbers, that gives us the set of integers. Okay, so you can see how we started down here at the bottom with natural numbers. So we started with a set of natural numbers. We added 0, and that brought us up to the whole number set. And then we added negative numbers to the whole number set, and that gave us integers. So what you could say is you could say that a natural number like 2, 2 is a natural number, but 2 can also be a whole number, and 2 is also an integer. Okay. So at this point, we kind of have to stop on this branch because now we're going to head into rationals. Okay. But let's stop at this point and let's go down here to fractions and decimals. So we spent a lot of time in this chapter or this section and the previous one talking about fractions, and we've been talking a lot about decimals. So we can have fractions like 1/5 and 1/3. Now, 1/5 is an example of what's called a terminating fraction, or a decimal that stops. So if we convert a fraction to a decimal, we can see that it stops at the tenths place. It doesn't keep going forever. And that's what we mean by terminating. Okay, the decimal stops at a specific fractional part or fractional decimal place. By contrast, the fraction 1/3, this is non-terminating and repeating. So 1/3, let's wait for my tablet to kind of catch up here. 1/3, when we convert that to a decimal, will be 0.33333 repeating. Okay, the 3 will just keep going off into infinity. Sorry, my tablet, I think, is overheating, so it's slowing down here. trying to select a different color, but it's not letting me. There we go. Okay, so 1/3 is 0.3 repeating, which means these threes just keep going and going and going. So that's what we mean by non-terminating and repeating. All right, so we can have fractions and decimals, and you'll notice that fractions and decimals, they do not fit. Fractions and decimals don't fit in the integers, they don't fit in whole numbers, and they don't fit as counting or natural numbers, because integers just have, they can only be a single number. They can't be expressed as a decimal. Okay, so that's why this branch of the flow chart is separate from this branch of the flow chart. All right, so now if you take the set of integers and you group that with the set of fractions and decimals, both terminating and non-terminating, you group all of this together, all of these numbers together, you get what's called the rational numbers. So an integer is a rational number. A whole number is a rational number. A natural number is a rational number. A terminating fraction or decimal is a rational number. A non-terminating and repeating fraction and decimal is also a rational number. So the rational number set is all of these numbers down below it. All right. And that's this branch here, which is kind of leading us to the definition of what a real number is. But before we go there, let's travel down and see what an irrational number is. So we have rational numbers and irrational numbers. And an irrational number is a non-repeating decimal, kind of like what we had down here, that cannot be expressed as a fraction. So, down over here on this side, we could express this decimal as a fraction. But irrational numbers don't allow you, they're actually, I wouldn't say don't allow you, they are just numbers that can't be expressed as a fraction. So for example, one type of those is like the square root of 3. Okay, we can't say the square root of 3 is equal to like the fraction, 1/3 or 1/41. Okay, we can't convert like this square root into a fraction. So any number that is non-repeating, a non-repeating decimal, and can't be expressed as a fraction like this is an irrational number. So one way of getting an irrational number is in the algebraic number set. Okay, and this is just a few examples of what we mean by an algebraic irrational number. Another way that you can get an irrational number is, I would say, from a symbol. Okay, but these symbols don't just fall from the sky. So for example, pi, okay, that's a symbol, and you've heard of it before, and you've probably seen it as 3.14. But 3.14, this is rounded. Okay, pi in truth just keeps going, and it doesn't repeat. It's a non-repeating decimal. And where pi comes from the ratio of circumference to the diameter of a circle. So if you take the circumference and divide it by the diameter of a circle, then you're going to get 3.14, and it just keeps going forever. Well, instead of working with a non-repeating decimal that just goes on forever, we just use a symbol to represent that. And so we use pi. So pi is represented as a symbol, but it too is an irrational number. And there's others like E, and there's a few others in here that kind of do the same thing. So these are all examples of irrational numbers. So now, let's see if I can use a different color. What would be a good color? How about Okay. So now if you take all of these rational numbers and you add to those all of the irrational numbers, the sets of those two is what we call the set of real numbers. So the real numbers includes all of those and all of those below it. So square root of 3, even though it's an algebraic irrational number, square root of 3 is what we call a real number. If we have the integer -2, this integer of -2 is also a real number. Our fraction of 1/3, which is a non-terminating and repeating decimal, that's considered a real number. So a real number is the set of numbers which includes all of these other sets below it. Okay, so that's fun. Now, if we go to, if we look above the set of real numbers, we can see that branches over here to complex. But before we talk about complex, let's go over here and talk about imaginary. Now, imaginary numbers are just represented with the letter I. And I kind of made this little label up just so that I could use it up above here. But imaginary number, you may have heard before that it's not possible to take the square root of a negative number, right? You've probably been told in the past, you can't do that, don't even try. But the truth is, you can do that. Okay, you just can't take the square root of a negative number and expect it to fit within the set of real numbers, because it doesn't fit in the set of real numbers. It doesn't fit down here, it doesn't fit down there, it doesn't fit over here, it doesn't even fit in the irrationals. Okay, it's its own kind of number. And it turns out that the square root of -1 is just I. Okay. If we were to take the square root of -4, that would be 2I. All right. Because you would write -4 as the square root of -1 times the square root of 4. And the square root of 4 is 2. And the square root of -1 is I. So you get 2I. So this set of imaginary numbers is distinct than anything else. So that's why it sits all by itself on this separate branch right here in this diagram. And so if you take a real number and you couple that with an imaginary number, then you get the set of what's called complex numbers. And so a complex number is a real number plus and minus an imaginary number. So technically, every single number that we described down here, down below, every single one of these can be considered to be a complex number, because this complex number set is kind of like the highest hierarchy above all of them. So I'll let that kind of gel and digest. You can rewatch this explanation, but I think that's probably the easiest explanation of each of these and how they're kind of all interrelated and how they fit within this hierarchy.